Everyone who falls from a plane falls at the same speed. The ones who survive are the ones who land on the right thing. And here's the part that will completely change how you think about this. The height doesn't matter, not really. A fall from 33,000 feet and a fall from a 2,000-foot cliff end at the same speed. The altitude changes how long you fall, not how hard you land. So the real question here was never, can you survive 33,000 feet? It's, can you survive 120 miles an hour? And what do 3 minutes of free fall do to you before you ever get there? That's what this video is actually about. And by the end, you'll understand exactly why some people have walked away from falls that should have been impossible, and why the one thing almost everyone thinks would save them is the worst possible choice. That answer is coming. But first we need to build the physics, because without it, none of the survival stories make any sense. Let's start with the fall itself. And the first thing that happens when you go out the door at 33,000 feet, you accelerate. Your body picks up speed fast, roughly 12 seconds, somewhere between 1,500 and 2,000 feet of drop. And then you stop accelerating. You've hit terminal velocity. From that point on, you are not getting any faster. The commonly cited figure is around 120 miles an hour for a stable belly-to-earth position in dense, low-altitude air. So whether you fell from 2,000 feet or 33,000 feet, you hit the ground at the same speed. The extra altitude just means you had more time in the air. That's it. But here's where cruising altitude gets genuinely strange, because the physics up there behave differently than most people expect. At 33,000 feet, the air is roughly a quarter to a third as dense as it is at sea level. Less air means less drag, and less drag means your terminal velocity up there is substantially higher, plausibly approaching 200 miles an hour, depending on how your body falls. So the fastest part of the fall isn't the end, it's the beginning. You spend the first portion of the descent accelerating to a speed well above what you'd reach closer to the ground, and then you spend the rest of it slowing down as the air thickens around you. You arrive at the surface at the normal 120, but you got there by first going much faster. The extreme version of this is what happened when Felix Baumgartner jumped from the stratosphere in 2012. He topped out at 843.6 miles an hour, about 1.25 times the speed of sound, during a free fall lasting more than 4 minutes. The air up there was so thin it couldn't break him fast enough, so his body passed through the sound barrier before the thickening atmosphere finally slowed him back down. 2 years later, in 2014, Google executive Alan Eustace jumped from an even greater height, more than 41,000 meters, and took the altitude record. Both of them were dealing with the same principle that applies at 33,000 feet. Thin air, less drag, higher speed. Now here's something else people get completely wrong about being thrown from a plane at cruise altitude. They imagine you'd explode or boil, the science fiction version, where decompression turns you inside out. That's not what happens at 33,000 feet. The altitude where body fluids actually vaporize, called the Armstrong limit, sits at around 62 to 63,000 feet. Cruising altitude is nowhere near it. What decompression at 33,000 feet actually does is much simpler, and in a strange way, much more relevant to whether you survive. It takes your oxygen away, and that's where the fall gets interesting, because you wouldn't be conscious for most of it anyway. At 33,000 feet, the time of useful consciousness, the window where your brain is actually working, is measured in tens of seconds, roughly 30 seconds to a minute under normal conditions, shorter after a rapid decompression, which strips oxygen out of your lungs faster than simply holding your breath would. The fall itself takes about 3 minutes, so you black out early, you fall unconscious through the majority of the descent, and somewhere in the low to mid-teens of thousands of feet, where breathable air starts returning, you may come around again. The terrifying 3-minute conscious scream that people imagine, that's not what this is. You're out for most of it. And here's the part that sounds wrong. Being unconscious and limp may actually work in your favor. A relaxed body distributes impact forces differently than a rigid, braced one. The instinct to tense up, to prepare for the hit, may work against you. Being limp is not the same as being dead, and in a fall, those two things are further apart than you'd think. But none of that is the main event. The main event is what happens in the last 1,500 feet, because that's the only part of this fall that was ever going to decide whether you lived or died. The number that determines everything isn't your speed, it's your stopping distance. Think about it this way. Injury isn't caused by speed. Injury is caused by deceleration, by how quickly your body goes from 120 miles an hour to 0. And deceleration is entirely a function of how far your body travels while it's stopping. Stop in 1 centimeter and the force on your body is catastrophic. Stop over 1 meter and that same energy is spread across a distance 100 times longer, which means it's far less intense at any given moment. Same speed, completely different outcome. This is the mechanism a US Air Force colonel named John Stapp proved in the 1950s, and he proved it by strapping himself to a rocket sled and riding it into a set of water breaks. He sustained 46.2 G when the sled stopped in 1.4 seconds, the highest deceleration voluntarily endured in a recorded test at that time. He survived it, but he did not walk away clean. He was left bruised and badly shaken, with burst blood vessels in both eyes and lasting damage to his vision. The reason he survived at all wasn't that the force was small, it was that the water brakes spread the stop over enough distance and time that his body could absorb it. The deceleration was controlled, it had room to happen. So now you understand the physics, and now the survival cases make complete sense. Every documented case of someone surviving a fall from extreme altitude without a parachute follows the same pattern. It's not about body position, it's not about technique, it's about what they landed on. Nicholas Alkemade was an RAF tail gunner who bailed out of a burning Lancaster bomber in March 1944 at around 18,000 feet, without a parachute. He fell through pine branches into deep snow and survived with relatively minor injuries. The branches slowed him. The snow gave him the stopping distance he needed. German captors reportedly verified his account by recovering his unused harness from the wreck. Alan Magee was a US B-17 gunner who fell from around 20,000 feet in January 1943 after his aircraft broke up over Saint-Nazaire in France. He crashed through the glass roof of the town's railway station. The glass gave way, the structure absorbed the energy, and he survived, badly injured but alive. Snow, tree canopy, a glass roof, deep marsh, soft earth, thatch. Every single surface that appears in these stories has one thing in common. It converts a centimeter-long stop into a meter-long one. There's no technique that saves you, there's only terrain. Which brings us to the thing I promised at the start. The answer almost nobody gets right. If you ask a room full of people where they'd rather land after a fall from altitude, most of them say the sea. Water feels soft, water feels forgiving. Water is the wrong answer. At terminal velocity, water is effectively incompressible. It cannot get out of the way fast enough. The stop it delivers is measured in centimeters, not meters, much closer to hitting concrete than most people imagine. The reason documented survivals cluster on snow, canopy, and soft structures is not coincidence. It's physics. Water is one of the worst surfaces you could land on, and it's the one most people would choose. Now, the story that ties all of this together, and the one that shows you exactly what survival actually looks like. On the 24th of December, 1971, 17-year-old Julianne Koepcke was on board Lancer Flight 508 when the aircraft came apart in midair at roughly 10,000 feet. She fell still, strapped into a row of seats. The bench of seats may have spun, slowing her descent. The dense, springy jungle canopy absorbed the final impact. She woke the next morning on the forest floor, broken collarbone, lacerations, alive. And here's the detail that reframes the whole video. She survived the impossible part in about 3 minutes, and then very nearly died doing the ordinary part over the following week and a half. She moved through the Amazon for around 11 days, surviving on sweets salvaged from the wreckage and on what she'd learned from her parents, who were both zoologists. Her father had taught her that following moving water leads to people. That knowledge, not the fall, not the physics, not the seat row, is what actually saved her life. The fall was the easy part. There's one more thing worth knowing, and it connects back to something in her story you might have skipped past. Look across every credible high-altitude survival case and you'll find the same detail. The survivor was attached to something, a seat row, a section of fuselage, a wing fragment. Wreckage tumbles rather than streamlines, which increases drag and lowers terminal velocity. And then, on impact, the structure crushes, absorbing energy that would otherwise go straight into a body. The instinctive fantasy is being thrown clear of the plane. Being thrown clear is the death sentence. The people who survived stayed strapped into the structure. Which brings us to Aloha Airlines Flight 243 in April 1988. A large section of the upper fuselage tore away at around 24,000 feet, The aircraft landed. The overwhelming majority of people on board survived. The single fatality was a flight attendant who was standing, not seated, when the roof went and was swept out. The entire difference between the survivors and the one person who didn't make it was a seatbelt. Not speed, not altitude, not luck, a seatbelt. So let's bring this back to where we started. Could you survive a fall from 33,000 feet? The physics say yes, with the right surface, the right stopping distance, and ideally something to be attached to on the way down. The altitude itself is almost irrelevant. By the time you're a few thousand feet off the ground, you are falling at exactly the speed you'd be falling if you'd stepped off a 2,000-foot cliff. The height just gives you more time in the air, most of which you'd spend unconscious anyway. The question was never about 33,000 feet. It was about the last 1,500, and then, in the end, about a single meter. 1 centimeter of stopping distance kills you. 1 meter might not. That is the whole game. That has always been the whole game. If this is the kind of breakdown you're after, there's another one on screen now that goes just as deep. And if there's a survival case you think should have been in this video, leave it in the comments. I read them and they shape what I make next.